Hi guys, welcome back to my YouTube channel. This video is going to be about my EEE-313 electronic circuit design term project in Bilkent University. The main objective of this experiment is to keep a specific resistor at a specific temperature. I used a K-type thermocouple to get that temperature information. And according to Thermocouple's information, the 18 volts voltage source feeds the heater resistance via an electrical switch, which in my case I used a BJT. The switch should turn on when the temperature of the resistance is below the desired temperature, and the switch basically turns off when the temperature of the resistor is higher than the desired temperature. Here you can see the LT-SPICE schematic of my circuit. The circuit consists of three main parts: the high-gain instrumentation amplifier, the comparator op-amp, and the switch mechanism. The thermocouple is a temperature measuring mechanism which gives a voltage difference in its two legs proportionate to the temperature that is measured by its head. The high-gain instrumentation amplifier takes these two thermocouple legs as its input, and it amplifies the signal. The gain is nearly 70 decibels, or in other words, the relation between the output voltage and the input voltage is nearly 4000. A comparator op-amp is connected to the output of the instrumentation amplifier. When the output of the amplifier is below a certain value, the comparator op-amp gives high voltage. And when the output of the instrumentation amplifier gives a higher value, the output of the comparator gets low. Since an op-amp cannot give enough current to heat up a resistor, I used a BJT just as a switch in order to pull the current directly from the DC power supply. Here you can see my dip trace schematic design. Notice how some of the resistor values are changed from the LT-SPICE schematic. This is because before designing the dip trace schematic, I tested the circuit on a breadboard and I had to tune some resistor values, and therefore this is the reason for this change. Here you can see the PCB layout both from the top view and from the bottom view. Notice all the traces are on the bottom layer, and the top layer only contains the drill holes for the components. Also, since the circuit is relatively easy, I only used one layer for the traces. So at this point, all the design was finished. It was successfully finished and it was working. After I managed to finish these schematic and PCB designs, I sent the Gerber files I extracted to my professor. He took care of the fabrication. After a few days of submitting the files, I got back my physical PCB. Now let's check the results on that PCB. As I turn the power on, the output of the instrumentation amplifier starts from 2 volts and goes up until 9 volts. Please look at the LED. At 9 volts, the circuit self-adjusts itself while turning off and on consequently. Now I'm going to talk about two major difficulties I faced while doing this project. The very first of them is the offset voltage problem. Since I was using a high gain amplifier, I had to take offset voltages of non-ideal op-amps, non-ideal real-life op-amps into account. The amplifying factor was so high that even those small changes in the millivolts level would affect the output. But not only using different op-amps give you different offset voltages. Using the exact same op-amp in another temperature gives you another offset voltage. It just fluctuates so much. For instance, when you first powered up an op-amp that has been resting for overnight, and after you use it for some 15-20 minutes, the op-amp heats up and the offset voltages change, so the results are not that consistent. The second major drawback I faced was in the PCB design. Well, when I got my fabricated PCB, there was a top silk layer, but there was not a bottom silk layer, and all the traces were actually visible on the bottom layer. So when I was desoldering one joint at one time, I actually desoldered the metal trace and then, had to solder it back again, and that was kind of a problem. So my advice for future projects, definitely put a bottom silk layer on that, because when you're trying to desolder, that way you wouldn't take out the trace from the PCB. So guys, this was the end of the video. Thank you very much if you watched till the end. And until next time, take care.